Hello and welcome to our webinar. I'm Pete Starkey, a member of the Council of the Institute of Circuit Technology, which is dedicated to technical aspects of printed circuit board manufacture and assembly. The Institute continues to successfully provide its members with opportunities to improve their knowledge of manufacturing process technologies, materials and practices, and to stay in touch with current and future developments. The future of printed circuit manufacturing and assembly will rely heavily on automation and the establishment of the smart factory. What will this involve, and what additional skills will engineers need to learn? A leading expert in this area is Happy Holden, Honorary Fellow of the ICT, who has kindly offered to deliver a series of 8 one-hour webinars based on his recently published ebook, 24 Essential Skills for Engineers, which is free to download from the iConnect 007 website, and which will form a valuable resource for in-house training of engineers and their career development. In his initial presentation, Automation and the Journey to Your Smart Factory, Happy introduced the elements of the journey and discussed the key issues: who, what, how long, when, and how much. In principle, he advises that you avoid factory automation consultants who will typically charge you for learning your processes and procedures while selling their own equipment and software. Instead, Happy suggests that you select your own engineers who are familiar with your own processes and procedures and let them learn how to do the automation planning. Then they can teach others this essential skill, which the factory will need over and over again. Last week, he examined the skills of benchmarking, product and process life cycles, engineering economics, and road mapping. In today's presentation, the 4th in the series, Happy turns his attention to defining automation and the automation methodology. If you have any specific questions, please direct them to happy@iconnect007.com. So it gives me great pleasure to hand over to Happy Holden. Happy.
Well, thank you, Pete. As always, excellent introduction. This will be an intense presentation today because I crammed a lot of slides into this, and so we'll get started right away. Like I said, this is the 4th on our series, Automation and the Automation Methodology. This comes from the other ebook I asked you to download, Automation and Advanced Procedures in PC Fabrication, from the 007 library, which is again free, as well as the other ebooks that we kind of use as reference for this presentation. Today I'm going to start a lot of what we call computer integrated manufacturing, because that's where I developed the automation planning methodology in terms of these 6 topics. I want to start with the Computer and Automated System Association, SimWheel. This was produced by SME in 1981. And if you look at that, this could be the logo for Factory 4.0, Industry 4.0, because this is what automation is all about. Factory information, product and processes, manufacturing planning and control, being driven by strategic planning, finance, management, and marketing. But like I said, this is over 40 years old, and probably was developed before some of you may have even been born. The CASA part of SME was founded in 1975. Core to their computer integrated manufacturing are these 7 areas: computer-aided design, group technology, manufacturing planning and control, automated material handling, computer-aided manufacturing, robotics, and computing technology. You're probably familiar with many of them, probably not group technology. Group technology is quite important, but somehow doesn't show up so much in this Factory 4.0, even though it's fundamental to product planning and automation. As head of the application organization in Hewlett-Packard, where we were helping companies plan their automation, group technology is a key contributor. I spent many hours at Caterpillar Tractor and John Deere, who have some of the world's most advanced group technology, helping them implement these databases from a design methodology, because they found out that 80% of the time they were designing parts that they had already designed but had no way of knowing. And by having a group technology methodology, before they started ever designing a new part or of a product, they would look and see if they developed it before, and lo and behold, they may have designed it 6 times, and so they just activated the most cost-efficient, highest quality one, and the design was finished. It's very, very powerful technology, but one that you don't see talked about too much today. This one isn't in your handout. I came across this and decided to throw this in because this is data-driven automation 1983 provided by the IEEE Spectrum. And just to show that, again, in the 80s when we started doing all of this, it was quite involved. And in fact, this is, you might say, the composite of a fabrication and assembly of complex products, going all the way through, including warehousing and the materials. But, I just thought I'd throw that in to see if your eyesight's okay. The Factory 4.0, which came out in Germany in 2012, it's been 52 years, and really nothing has changed but the buzzwords, and especially the costs. It still comes down to business fundamentals, common sense, and planning, but it's cheaper now, and you have more competition and choices. Interesting enough, they, since they came up with Factory 4.0, which they tried to tell everybody was brand new, they went and changed all of the buzzwords that we had in the 80s. So sim evolution then became the digital factory, digitization in the cloud. The computer integrated manufacturing hierarchy became a multi-layer functional hierarchy. SIM and CAM architectures replaced with ISA's 95 architecture. SIM connectivity, which 40 years ago was RS-422 or 232, now becomes Ethernet and Internet of Things and 5G wireless type. And SIM simulation, which was a particular area that I focus on, now is called digital twin, interesting enough. But if you're wondering about digital twin, look up SIM simulation and software that's already existed for the last 10, 20, 30, or 40 years. But the whole SIM process is the same as the smart factory process. It starts with planning and business planning from a strategic point of view, and then moves down through until you get to the tactical area. If you don't do it yourself, like I said, there's management consultants, manufacturing consultants, technology consultants, automation consultants, and then the particular vendors and that sell the products. One that you may have a hard time finding is an automation consultant that knows anything about printed circuit fabrication or printed circuit assembly and box build, which is why I emphasize that in many ways, if you take a good process engineer or product engineer in your company, in many ways, I think it's easier to teach them the fundamentals of automation and automation planning than it is to try to find the right kind of automation consultant. Even though, like I said, you may have very successful management consultants or technology consultants in years from strategic to the tactical area. So the sim-directed manufacturing planning facility has, 6 stages from environmental assessment, which is what I've been calling your strategic business plan or performance plan, something like that, all the way through program strategies, conceptual design, detailed design, development, and then implementation. With this, this hasn't changed at all since, I've been using this for the last 40 years. The enterprise and plant topology fundamentally hasn't changed from the factory floor. We have the device and level sensors and devices and machines sitting on the factory floor. Then you have a control level that are machine coordinators and controllers. And above that, manufacturing execution systems for global operations. And above that, enterprise resource planning, ERP levels, with communication layers between each one of them. So we'll talk more about the communication on next lecture. This one is kind of more fundamental. So there's a hierarchy of activities and systems from the machine sensors and actuators all the way up to the smart instruments and microcomputers and NC controllers to the supervisory control level, to the manufacturing control level, and then the financial planning, manufacturing planning and control. And then off to the sides, research and development for new processes or products that interacts with which each level in the hierarchy. So the SIM hierarchy of activities, has to do with work centers where you do the work and you collect the data, from raw materials coming in and then finished goods going to customers on the way out, and then orders and through marketing and sales and specifications from higher level, where you're working on control and direction based on data, coming up from the various levels of the hierarchy. Another way of looking at this is at the top is our strategic plan, as I mentioned before, the business plan that drives all of this, and then customer feedback and proposals and performance and simulations and what and when, and quality performance and how much, and products and competitions, all fit in with the overall data requirements. Many times the SIM solutions for this, involves, both the planning, the control, the monitoring, and then the systems management. And there are generic interfaces and specifications depending on the equipment, processes, devices, sensors, and material handling. And as you see here, the protocols and the connectivity of this can be quite different. And we'll cover those in the next lecture about, MAP, OML, IEEE 488, Ethernet, GEMS, SEX, CFX, etc. Getting more back into our area, CAE, CAD, and CAM of the information flows of printed circuits and assemblies is one of, very dedicated databases and materials and systems specifically to handle the standards and the process data and component data, that is manipulated by engineering and it's stored and then provided, to the factory floor whenever it's required. So the automation methodology for work centers, and you all have process diagrams of how your products are built in terms of work centers or things like that. What we did to simplify the planning is that we looked at automation and realized that automation is a combination of mechanization and the system information for that mechanization. And so it's a vector. So we chose 6 levels of classes, A through F, for mechanization, and 6 levels of information, 1 through 6. And then we, as we'll go into, broke what happens at a work center down into these, 2 levels of documentation. There are 2 additional dimensions, and that is between work centers, there's material handling for the mechanization, and between information at each work center, there's the role of networking. So mechanization class is, manual, semi-manual, machine-assisted, human-assisted, semi-automatic, and fully automatic. And it's basically defined as the percent done by machine. So manual, 0 is done by machine, whereas in semi-manual, 1 to 24% is B, all the way up to F, the fully automatic, which is 100% done by machine and 0 done by the human. So this kind of describes that, actions conducted by the human with simple tools, action conducted by humans with complex tools or machines, some activity part of the heart, all the way down to F, where all actions are done by autonomous machines with minimal or no human role involved. And the systemization levels are equally. Number 1 is manual information collection and distribution, which is essentially distribution of paper or work center information, which an operator reads the work traveler and sets up a machine or something else. That's 0 is done by sensors or computers, all the way up to level 6, which is a fully automatic gateway network, whereas 100% is done by sensors or computer and 0 is done by humans. And again, the definitions, where you set parameters, record past occurrences, documents produced at something, including things like visual inspection and things like that, all the way down to the fully gateway network system, which is information management executed a control action when predefined conditions are occurred. So how to improve automation? Well, under the mechanization, you many times add new equipment, which might be loaders or unloaders or stackers or conveyors or robots, automated guided vehicles, or some other carts. Whereas in systemization, you may add RFID or drill codes, barcodes, or readers with sensors through data acquisition equipment, interfacing data acquisition to existing equipment in order to take that information and put it into the system. A new one called inline confocal sensors is an IoT technology that is a sensor that you buy that can scan an entire PC board or assembly on a conveyor and be programmed to do particular measurements or other types of information and provide that back to it. This is not an AOI machine. This is just a sensor that could be incorporated in AOI machine, but they're far less expensive and they're essentially designed to go onto machines or onto conveyors, as well as white light interferometry and networking lab prototype equipment. So the automation strategy and planning is one of breaking down your work center into individual activities with that. And then, how much is done by human in terms of mechanization, how much is done by humans or machines in terms of the information that drives that work center. And then between work centers, you have the material flow, and for the information flow, work center to work center. So this network communication information has a systemization level, working with mechanization classes, supported by material management handling, which is degree A through F, and network communication extent 1 through 6. So these are the 4 degrees that make up automation in many ways that we'll talk about today. So, like I said, the part of that is breaking down the work center in terms of currently what you have, be it soldering or cleaning or touch up or in-circuit test or electroplating, et cetera, et cetera. And then benchmarking where you are today, right now. And then looking at your plans and improvements, where do you want to be in phase 1 or phase 2 or phase 3 in the future in terms of that. And we do that with worksheets that I'll get to here. But you can see here that it may not be possible to go from manual to fully automated facility in one jump. But if you're, depending on where you are, your customers, what equipment you have, the people you have, it may be one of various phases in terms of phase 1, phase 2, and phase 3. I've indicated here with the blue circle, red square, and the green diamond, as well as material handling between these work centers, and then communication extent between these work centers. What I mean by that is this is one of my process diagrams. I have printed circuit multilayer manufacturing broken down into 200 separate slides like this, into enormous nuance, in order to help people, understand that each work center may consist of a couple of activities or multitude of activities and steps. And here you can see, I'm talking about multilayer layup, 2.2, 2.3, 2.4, 2.5, in my process diagram. And then from that, you look at benchmarking. Where are we right now in terms of the interlayer preparation or the interlayer connections, lamination layup, and or lamination, and what is the material handling between each of these more defined steps in multilayer layup, and what's the role and how is the information passed along and provided with that. And so this is where you start getting into the automation strategy and planning by looking at your particular work center in terms of your current, and then starting to theorize what are the new improvements or the future, including multiple, this is phase 1 or phase 2 or phase 3, that you're looking to achieve. I do this by a worksheet like this, where I have, the process description, and the process step number, and then for the mechanization classes, actually go in and time what the people are doing, including um, all the people. So the human setup time may be 6 minutes, and we'd like to reduce that to 1 minute. The machine setup time maybe 2 minutes, and in the future you would like to do that to 1 minute. But the runtime after setup, the human may put in 20 minutes, and in the future we'd like only 5 minutes, and the machine provides 12 minutes, and we'd like that to increase to 34. So we want to go from 35% to 85%. And then so the total human time, summing the setup and runtime, and then the total runtime, and then the mechanization class, that the same thing is done for information. If you have to read a particular work order in order to know what material or everything else, then the amount of time spent by the human currently, and how much do you want to do in the future? Then summing that up, the total human time involved and the total runtime involved, as well as defining the material handling degree in terms of how much time is involved in actually moving the materials or the multi-layered plates, et cetera, between these different operations currently and what we would like in the future. And then, how is that information conveyed between the information, via voice or additional paperwork or logs, et cetera, and what would you like that to be in the future? So, here's step 2-3 in terms of moving from mechanization class C with, basically no systemization to mechanization class E and fully automatic gateway system, in which you want the human time in the future to essentially be 0. In the current, it's 10 minutes for the systemization level, but the future you want it to be 0. And so there's the things. And then as you look at the networking and the material handling, this will begin to show you the extent of what projects and everything else you have in front of you. Further, process step 2-4, again, measuring the human and the machine times, the information from the human and machine currently, and then what you might want in the future. You can see that a number of these are set up for mechanization class Fs. So they're going from a B, which is about, semi-manual techniques to fully automatic techniques. And this may be because of a new machine or machines available that are currently on the market, or ideas that you have to mechanize this, or provide through sensors and data acquisition, the information automatically running. And then process step 2.5. Here we're talking about introducing a new induction lamination vacuum press. Unlike the heated, this new technology, every single multi-layer has its own set of call plates, because the stainless steel separator plates through induction heat up and provide the heat individually to every single multi-layer. They're all identical, and it can do this precise control and precise temperature monitoring, incredibly productive, as well as 1/50th the amount of energy involved in heating and cooling. And then at the systemization level, proposing the GEM interface to the management and management equipment management system, and then using a powered conveyor, and again, the GEMS interface on systemization level. So automation strategy and planning is, is involved. A lot of that, it doesn't involve the actual benchmarking how you manufacture. It's doing the audits and the environmental assessment based on your business plan, based on your customers, based on your materials, based on your finances, and things like that. It's important. And one of the reasons we're running this seminar now is that in the next 2 to 5 years, the entire world is focusing enormously on semiconductors and semiconductor packaging. And so there's an enormous opportunity for money involved. Here in North America, our Congress passed a 200 billion technology bill. Out of that 200 billion, 50 billion is focused on semiconductor production in North America and the packaging. But as part of that 50 billion and part of that 200 billion is the infrastructure of electronics in general, that is circuit board fabrication and printed circuit board assembly. And so as other countries and everywhere else begins to focus on that, there's going to be a lot of money available. And so now is the time to kind of get your ducks in order and figure out, what is your business plan for the next 5 years in terms of taking advantage of this unique activity and operations. If you've read the IPC thought-provoking things written and available, the IPC Board of Directors is actively lobbying for grants and investment of $10 million per printed circuit fabrication, with 7 to 10 printed circuit fabricators being identified to receive the $10 million of investment money minimally in order to bring them up to the state-of-the-art level that we need to match the semiconductors that goes on. So, the people involved, like I say, work from senior management, the business planning staff, senior operating staff, local functional staff, and then the technical staff in terms of, what is business driven in this automation strategic planning there on planning and defining, and what is technology driven and the other things. And so it's a role that starts from the tops down in terms of senior management, but you also need from the bottoms up the engineering that's going to do the technology driven parts of automation methodology and planning. And together, you can put together quite an effective program. Printed circuit manufacturing at Hewlett Packard, which I got involved with in 1970. I started in semiconductor thin film at Hewlett Packard, but within 6 months after HP had asked me to go down and help out the printed circuit manufacturing people. And first thing I asked is, remind me again, what was a printed circuit? But yeah, in 1972, HP introduced the HP 35 scientific calculator, which I think started the age of miniaturization is born. You can see that calculator there in the lower right. Within 3 years later, the programmable pocket calculator there next to it on the left. And this was made up of 2 printed circuit boards, an 8-layer multi-layer seen there in the middle, and then the double-sided keyboard and display driver in the upper right. Really interesting because one of our biggest problems was finding a reliable small switch for a keyboard. Nothing existed. I mean, at the time, the best we could find was a typewriter keyboard, the IBM Selectric, but it was 5 times thicker than the entire calculator was supposed to be. And so our mechanical engineers came up with what you see in the upper left there, which is annealed beryllium copper plated with gold. And then we would parallel gap weld those strips of beryllium copper to the printed circuit board below that. We had dozens and dozens of warehouse filled with HP XY plotters with parallel gap welding heads in order that we had everybody in the Western United States making the 8-layer multilayer in the middle. Because we were told when we were inventing this that we were lucky to sell 400 a month because they were $400. And well, 400 a month was great for us because that's like the run of a popular voltmeter or something. Instead, within a year, we were getting 3,000 an hour, far different than what they predicted at 400 a month. So in '73, the orders were so large that Hewlett-Packard sent Clyde Coombs to Singapore to see if they could be made there. And the government offered HP a 5-year tax-free if they would make the calculator with 27% Singaporean content. Unfortunately, the assembly labor cost was not 27%, but if we added in the printed circuit board to that from Singapore, and so my group was challenged with designing a printed circuit fabrication facility for Singapore, its first. And 3 of my engineers took a 3-year leave of absence to start up and run that facility, for the company that we found in the Bay Area that wanted to move to Singapore. And HP would purchase 65% of their output for the next 7 years. By 1978, HP had me develop a state-of-the-art PC fab in California, and this was our first highly automated computer-controlled manufacturing. By 1980, HP Taiwan led a government study tour of HP, including the Sunnyvale. And in '83, I led a government study to find an RSC corporation that could build the complex multilayer HP needed for computers. And I worked, interesting enough, with TSMC, which was just starting up at that time. So an industry kind of 3.4 example, which was in the mid '70s, was one of my first projects in terms of automating the entire electroplating. This random input-output electroplating has 4 different final finishes that you can call out. And it's entirely driven by a barcode system in terms of one of the first computers ever applied in electronic manufacturing, including metering pumps for the chemicals and control of all the rectifiers, which is interesting enough. For Hewlett-Packard rectifiers, these were 50 and 100 amp HP rectifiers, which I had to order nearly 2 years in advance in order to get the number required to run a large electroplating line like this. But at the same time, Hewlett-Packard has one of the biggest semiconductor fabrication in the world. And we started automating the IC fabrication in the early 1980s, that you can see here in terms of planning and control, manufacturing, engineering, and supervisory monitoring and control for semiconductor manufacturing. And this proved very useful because everything that developed for IC fabrication automation could be used for printed circuit fabrication automation. We just changed from wafer to panel and from die to board. But essentially there are many, many similar photolithography, electroplating, and other activities, paralleling that for the circuit manufacturing. With that was developed by SEMI the GEM standard of communication and protocols between the host computer to the actual equipment and on the factory floor using this 6GEM driver. Because of this, in the early 80s, Hewlett-Packard created what they called the Manufacturers Productivity Network. And HP went into the business of selling automated factory solutions. In other words, operation planning and control, all these different software, administrative and office services, computer-aided engineering, and factory and plant automation. At that time, Hewlett-Packard actually had CAD system software for sale, as well as mechanical engineering software and microprocessor design software. And so this MPN became a major program, of which, I ran the application organization that provided the application services to people interested in buying this from Hewlett-Packard. You can see these are different ones. We had 6 different printed circuit fabrication facilities around the world. All of them got involved with automating the factory automation systems for printed circuit manufacturing as well as electronic assembly. So we had this in Sunnyvale, California, Palo Alto, California, Hoboken, Germany, Boise, Idaho, Puerto Rico, Tokyo, Japan. We're all set up through my organization, kind of what we call the Industry 3.75. This is in the 80s in terms of using the methodologies and Hewlett-Packard computers and software, as well as a lot of custom written software in order to have a fully manufacturing integrated system. And you can see the modules here in a lot more detail in terms of information flow, and 14 different pieces of software that Hewlett-Packard sold at the time. None of those are available today, interesting enough. But in the 80s, those were key software, and one of the few vendors around the world that had such an extensive set of software for factory automation. When we did the Sunnyvale one, we kind of, using the methodology of breaking things up into manufacturing, engineering, and tooling, mechanical fabrication of routers, multi-layer presses, AOI, drills, and then chemical process control, and then product test and AOI and electrical test methodology. At the time, we didn't have this, but by 1995, the Europeans had established this ISA 95, which codifies this 4-level hierarchy of from sensing on the factory floor all the way up to manufacturing operations and business planning and logistics that now make that up. There are, at the time, numerous factory standards, protocols, and networking. These are just some of the ones that we'll talk about in the next lecture. In terms of, for robotics, it was the MAP standard, but for surface mount, IPC CFX. For field sensors, it may be IEEE 48. For programmable logic controllers, it may be Profinet. On and on and on. The details will lead to the next lecture. As well as companies starting to develop their proprietary ones. This is the Panasonic SIM system, which is proprietary. It's interesting that although it's proprietary, it will take their proprietary or the Sex2GEM standard from SEMI. And you'll see, because the Sex2GEM standard was developed in the early 80s and has continued to evolve to run all wafer fabs, as well as photovoltaic manufacturing and LCD liquid crystal manufacturing. So they've had nearly 40 years to perfect software and control through the semiconductor networks. One of the biggest focus today is that of planned maintenance and moving towards predictive-based maintenance. If you're having more and more of this automated system, you certainly become more and more sensitive to unscheduled downtime. And so predictive-based maintenance is really, really an important factor as you focus more and more on automation. As an example of this, I don't know if you've seen this or not, but I like to show the Industry 4.0 example of Whelan Engineering, and their facility in Charleston, New Hampshire. Whelan has a printed circuit multi-layer fabrication operation, and there are nearly 120 code readers for their products you see here. They have a DMC code, drill code that are drilled in, and then barcodes as well as RFID devices, and then these readers all around the facility. So this is kind of the facility that I visited, spent a whole week there in 2016 at Whelan Engineering. You can see that. This is kind of different shots of the facilities, multi-layer, et cetera, et cetera. That's available in various iConnect 07. One of the most interesting one was provided by Exact there in the UK in terms of their software that learns from AOI and other types of measurement machines and predicts and provides measures and yield improvement, which is significant for that. The interesting thing about Whelan is was the pilot plant, which is a 50 panel per hour facility. It had no production operators. There were 17 technicians working on it 24/7. They had no effluent, 100% water recycling, and about 70% chemical recycling. And the copper recovery from etching is actually a profit center that pays for virtually everything else. And they put this together because they were making multilayers at half the price of China in 2 days instead of 12 weeks. And so with that, I want to show you this just 3-minute video. When you're watching this, remember what we talked about in benchmarking in terms of there is no setup time here. Once material is launched, there's no place for it to go. They only have a 1 hour worth of stackers you can see there. And the reason they have the stackers is they run 5 different kinds of printed circuit multilayers, flex rigid, metal core, and they run them on a random basis so that the stackers can hold them and optimize production. But once material is launched, the multilayer is shipped in less than 5 hours. There's no place else for it to go. And so untouched by human hands, including no visual inspection required, because the sensors are better than human eyes are. And they pretty much showed their customers and what they've done that our sensors are more reliable than human eyes are in terms of reliability. So here's 3 minutes. But again, watch for some of the things. Like this thing automatically racks and unracks 5 different final finishes. There's an automatic racking machine from a conveyor. that was my last slide. But one thing to keep in mind in terms of benchmarking is when they launch the material, the board never stops. So within 3, 4, 5 hours, depending on the lamination cycles involved, it's shipped. If you don't manufacture all of your products in 3 or 4 or 5 hours, then this is clearly the benchmarking that could be achieved. You may do it in phases. The other thing is that their yields are typically 99.8 involved, and that's because of the information and the software required that does predictive digital twin and corrects itself and improves registration, et cetera, in all of these. And so you can find there are nearly 8 different articles from 2015 on in the 07 magazines talk about the process of benchmarking. This facility, when it was up and running, had a payback period of 2.5 years and an extremely high ROI over bringing all the production back from China and Asia, providing more flexibility, higher quality, and the ability to have complex multi-layers, at half the cost of the best prices out of Asia. So with that, I want to thank you for your time. Our next week we'll go into the Smart Factory and talk about what happened to the Wheeling facility. 2015, it was a pilot plant. In 2018, they did a 5-fold expansion and built a new state-of-the-art plant that will have a video at the end of next week that, again, uses less water than the toilets for a facility 5 times larger, 100% recycle. And again, without operating labors, and yet capable of 4-micron lines and spaces, as well as multi-layers at 0.4 millimeters thick all the way up to 6 millimeters thick and 36 layers with blind and buried sequential lamination. Again, all done automatically. With that, thank you for your time, and I hope to see you next week.